Hello and welcome back to the Deep Dive, where we take a mountain of information and distill it into those essential nuggets of knowledge you need to be truly well-informed. I'm Nikhil Kamath, and today we're plunging into a topic that's buzzing with both incredible promise and, well, daunting challenges. The world of robotic startups. It's an industry that's captivated our imaginations for decades, hasn't it? Promising everything from, advanced factory automation to seamless household assistance. But the reality, as our sources reveal, is far more complex than the sci-fi dream. Much more complex. In fact, a staggering 99% of robotic startups reportedly fail. 99%. So what's really going on here? And what does it truly take to succeed in such a demanding field? To help us navigate this intricate landscape and give us the true deep dive, we have an incredible expert with us today. Welcome.
Thank you. It's a real pleasure to be here to unpack this fascinating high-stakes domain. Those numbers do tell a stark story, don't they? But they also highlight the immense opportunities for those who can truly understand and, overcome the unique hurdles.
Exactly. Today we're going to explore those hurdles in depth, from the financial black holes that, well, swallow ventures whole, to the complex technical challenges and the surprising issues with market adoption. We'll look at why so many promising ventures end up in what some call the robotics graveyard. Grim term. But it's not all doom and gloom. We'll also reveal the blueprints for success, focusing on innovative business models like robot as a service and the game-changing role of AI, particularly video understanding, in shaping the future of robotics. Our deep dive today draws from comprehensive research analyses, industry reports, and detailed case studies to give you a complete, actionable picture. Okay, let's unpack this challenging reality then. 99% failure rate. That's substantially higher than the general startup failure rate, which is often quoted around 90%. What makes robotics so uniquely difficult? What are the primary reasons these ventures struggle so significantly?
Yeah, that's where it gets really interesting and frankly quite brutal. It's not one single factor, but more like a cascade of interconnected issues. Together, they form what we often refer to as the robotics gauntlet. It's a tough path. Our research identifies 4 primary failure modes, each a formidable hurdle on its own. The first, and arguably the most immediate and unforgiving, is financial, what many in the industry call the capital chasm.
The capital chasm.
Yeah.
Sounds ominous. What exactly is that, and why is it such a problem for robotics specifically?
Well, think about it this way. Robotics is just inherently capital intensive. Unlike a pure software venture where you might build a product with just a few engineers and some cloud servers, here you're dealing with physical products, hardware.
Right.
That means every single aspect of development is exponentially more expensive and time consuming.
So it's not just code on a screen. You've got physical prototypes, materials, all that stuff.
Exactly. First, consider the talent required. You don't just need software engineers, which are, let's face it, expensive enough. You need multidisciplinary teams, mechanical engineers designing the physical form, electrical engineers for the circuitry, and then these highly specialized AI and machine learning experts to make the robot intelligent. All of these professionals command high salaries, naturally. And that directly translates to a high burn rate and a much, much shorter capital runway for a startup.
The clock is kicking faster.
Much faster. Then there are the physical products themselves. Prototyping isn't just, compiling code and pushing an update. It involves costly components, specialized sensors like LiDAR or advanced cameras, complex fabrication processes. Every single iteration of a physical robot, every tweak or improvement can be orders of magnitude more expensive and time-consuming than a simple software update. That fail fast, iterate quickly mantra, which works so well in the software world, it becomes financially perilous, almost deadly in robotics.
So that agile, lean startup approach from software almost works against you in hardware.
Oh.
It's a liability.
Precisely, it can be. And the R&D cycles, they're notoriously long. We're talking measured in years, not months.
Yeah.
To go from a conceptual lab prototype, something cobbled together, to a reliable commercial-grade product that's ready for prime time, that takes significant, sustained effort. And during this prolonged pre-revenue phase, these startups are just burning through capital, gallons of it, without generating any income. This extended timeline, it really tests the patience of venture capitalists. VCs are often accustomed to much faster returns in software investments, usually looking at, say, 5 to 7 years.
Right.
They're built for speed, and robotics demands patience. It's a fundamental mismatch.
And what are the real-world consequences of that for funding? Does it, actively deter investors?
Oh, it absolutely does. This challenging financial environment has very tangible consequences on the investment landscape. While the total investment in robotics can seem robust, I think it was around $18.5 billion in 2022, though it did fall to about $10.6 billion in 2023 and $9.7 billion by July 2024. A large portion of this funding is heavily concentrated. Much of it goes into a small number of late-stage, high-profile companies, often closing rounds of $50 million or more. Big checks for the big players.
Okay.
This creates a severe funding gap for early-stage ventures. It makes it exceedingly difficult for them to secure the meaningful financing needed to survive those initial R&D-heavy years.
The so-called valley of death is deeper for robotics.
Much deeper. And the lack of a consistent track record of successful M&A exits or IPOs in the sector, that further fuels investor skepticism. It makes them hesitant to back unproven ventures. You see real-world examples like Nauticus Robotics and Kodiak Robotics highlighting this. Both reported accumulated deficits of over $268 million each as of December 2024, and had substantial doubts about their ability to continue operations. That truly highlights the extreme financial fragility.
So to distill that, it sounds like robotic startups are fighting a multi-front war on capital. Not only is the sheer cost of building a physical product astronomical, but the investor patience required simply isn't aligned with traditional tech VC expectations. It's a fundamental mismatch between hardware realities and software funding models.
You've nailed it. That's the core of the capital chasm.
So even if they somehow clear that massive financial hurdle, which itself seems like an impossible feat for most, what's the next big trap? What catches these promising robotics companies next? It sounds like there's always another obstacle waiting.
You're absolutely right, there is. The next major pitfall is what we call the product market fit paradox. Basically, companies building technologically brilliant products that ultimately nobody wants to buy, or at least not enough people want to buy them to sustain the business.
Ah, the classic startup problem, but maybe amplified here.
Exactly. It's common across startups in any sector, but in robotics, it's particularly acute. The reason often boils down to the founders. Many robotics founders are brilliant engineers, truly visionary, but they aren't necessarily seasoned business strategists. They get captivated by the sheer technical challenges, the complexity, the cool factor, and this often leads to what's known as a solution in search of a problem.
A solution looking for a problem.
Yeah.
So they build something amazing, technically speaking, but it doesn't actually solve a real-world need, or not a pressing enough need.
Precisely. They might develop these over-engineered general-purpose robots that solve, diffuse or hypothetical problems, rather than addressing acute, high-value customer pain points. The key advice for any startup, really, is that your product should be a painkiller, not a vitamin.
Painkiller versus vitamin. Explain that.
A painkiller solves an urgent, acute problem that customers are desperate to alleviate. They're actively looking for a solution and are willing to pay a premium for it. A vitamin, on the other hand, is a nice-to-have. It offers incremental benefits. It might be cool, but it isn't truly essential. People can live without it. Many failed robotics ventures, especially in the consumer space, have unfortunately been vitamins. Very expensive vitamins.
Can you give us some examples of that?
Yeah.
Where the tech was cool, maybe even got a lot of buzz, but the market just didn't bite.
Certainly. Take the case of Jibo, for example. Remember
What's
Jigo?
Stigley, the little social robot?
That's the one. Highly publicized social robot, managed to raise $73 million. Technologically novel, got a lot of media attention, charmed many people. But it ultimately failed because it didn't solve a truly compelling problem for consumers. It was an interesting, perhaps even cute toy, right? But its core functionality was quickly surpassed by cheaper, more utilitarian devices like the Amazon Echo, which offered more practical value for a fraction of the cost. Jibo was a fun vitamin. People really needed a painkiller for information, music, smart home control.
Okay, that makes sense. Any others?
Another compelling example is Anki. This company raised nearly $200 million with its popular Cosmo and Vector robots.
Oh, I remember Cosmo. My kids loved that.
Right. They were sophisticated, AI-powered consumer toys, and for a while they were incredibly popular. Cosmo became Amazon's best-selling toy in the US in 2017, I believe.
Ugh.
However, the novelty eventually faded. These products, despite their high-tech appeal, lacked deep, persistent utility to justify their premium price. The high R&D and hardware costs associated with developing such complex robots simply couldn't be sustained by a business model reliant on one-time sales of products whose perceived value diminished over time.
So the excitement just wore off.
Exactly. This led to their collapse in 2019. It's a classic vitamin scenario where the initial wow factor wasn't enough for long-term viability.
And what about in the industrial space? Was it a similar problem there, or did it manifest differently?
It was similar in principle, but with different nuances. Consider Rethink Robotics, a real pioneer in cobots, or collaborative robots, with their products Baxter and Sawyer. Their initial strategic error, looking back, was focusing too heavily on achieving a low price point for Baxter. This led to compromises in fundamental performance characteristics, things like precision and reliability.
Ah, so they sacrificed core function for cost.
Arguably, yes.
Okay.
While the concept was innovative, a robot that could work safely alongside humans, these robots didn't meet the baseline industry expectations for consistent performance that manufacturers truly needed. They became more of a vitamin for manufacturers who really needed a painkiller, consistent, reliable automation to solve acute labor shortages or boost efficiency significantly. This allowed competitors, notably Universal Robots, to dominate the market. UR prioritized performance, precision, and ease of integration, even at a higher initial cost. They delivered the painkiller.
So it's not just about the idea, but the execution and hitting the real pain point.
Absolutely. Misjudging market timing and value, launching products too early or too late, or pricing them higher than their perceived value, all these lead to low adoption, regardless of how sophisticated the technology might be.
That's a very clear explanation. So, okay, let's say a company somehow manages to clear the financial hurdle and actually builds a painkiller product the market genuinely wants. They've dodged 2 bullets. What's the next challenge on this gauntlet? It sounds like there's always another obstacle.
You're absolutely right, there is. Even with a great product that solves a real problem, the business model void can sink a startup. The robotics industry as a whole still largely lacks mature, proven commercialization strategies compared to, say, SaaS software. Many ventures fall into the trap of a hardware-centric, upfront sales approach, just selling the box.
Right, the traditional way.
But the high upfront capital expenditure, the CapEx, for customers is a major deterrent, especially for small and medium-sized enterprises, SMEs, who might benefit most from automation but simply lack the budget for a huge initial outlay.
So it's not just about building the robot, but how you structure the deal, how you sell it and support it.
Exactly. It's the whole package. This upfront cost is compounded by notoriously long and expensive sales cycles. Think months, even years, and protracted pilot programs, too. These pilots can drain a startup's limited resources for a long time before a significant deal actually closes. It's not like selling software that you can download and test in an hour.
Much more friction involved.
A ton more friction. And beyond the initial purchase price, there's the total cost of ownership, or TCO. This is often underestimated by both the customer and, crucially, sometimes by the robotics startup itself. Integrating new robotic systems into a customer's existing, often legacy, workflows is incredibly complex and costly. It usually requires specialized integrators and significantly disrupts established operations during the transition.
Headaches for the customer, basically.
Big headaches. Then there are the substantial ongoing costs for support, maintenance, software updates, retraining staff. This creates a significant operational burden, potentially for the startup too if they offer support contracts, that traditional hardware sales models don't account for well. This high TCO makes it difficult for customers to achieve a rapid and clear return on investment, which in turn hinders scaled deployments. They need to see the value quickly to justify the disruption and cost.
Can you give us an example where the business model itself, rather than the tech or the product, was the core issue that led to failure?
A really stark example of this is Olive AI. They were in the healthcare AI space, not strictly robotics, but the principle holds. They collapsed despite raising nearly $1 billion in funding. $1 billion. Their downfall was largely attributed to an inconsistent and unsustainable business model. It proves that even massive capital infusions cannot overcome a fundamentally flawed commercial strategy that doesn't deliver clear, quantifiable value to customers quickly and reliably enough. And Rethink Robotics, which we just discussed, also struggled here. Their cobots, while innovative, couldn't consistently meet those industry expectations for precision and reliability. This undermined their entire business case and their ability to secure widespread adoption, despite the technical promise. The mismatch between perceived value and actual cost, complexity, and performance simply proved insurmountable for their sales approach at the time.
That's fascinating. It's like a three-legged stool tech, market fit business model, and if one leg is weak, the whole thing collapses.
That's a perfect analogy.
So we've talked about money, product market fit, and the business model itself. Finally, what about the broader environment? The ecosystem these companies operate in. Is that itself a major hindrance to success in robotics?
Absolutely. That's the fourth critical mode of failure we identified: ecosystem immaturity. Robotics operates on, let's say, unstable ground compared to mature software industries that benefit from decades of established platforms, standards, and channels. Probably the biggest handicap is the lack of common development platforms. Unlike software developers who can leverage mature operating systems like Windows or Linux, cloud services like AWS or Azure, and vast open source libraries to accelerate development.
They stand on the shoulders of giants.
Precisely. Robotic startups often have to reinvent the wheel. They spend inordinate amounts of time and expense developing foundational hardware and software capabilities, basic navigation, manipulation, perception that aren't core to their unique value proposition. While ROS, the robot operating system, has certainly helped create some common ground, it's still nascent and sometimes fragmented compared to the robust ecosystems available in the software world.
So they're effectively building everything from the ground up, including the foundations, rather than leveraging existing tools and frameworks. That must be incredibly inefficient and costly.
Hugely inefficient.
And this immaturity extends beyond development into the go-to-market ecosystem as well. Distribution and partner channels for robotics are just not as well established as they are for, say, enterprise software. Startups often have to build their entire sales and support infrastructure from scratch, which is another costly and time-consuming endeavor. And finding qualified system integrators, those crucial third-party companies that help customers install and integrate complex automation systems into their factories or warehouses, is also a significant challenge. The people who actually make it work on the factory floor.
Exactly. A McKinsey survey, for instance, found that 42% of industrial companies struggle to find holistic solution providers who can support them across different geographies and technologies. It's a very fragmented market for implementation partners. And then there's the human element: customer resistance and integration complexity. Integrating robots often requires a fundamental redesign of a client's workflow. This isn't trivial. It can be met with fear and resistance from workers concerned about job displacement, a very real concern, and also managerial hesitation to disrupt established, comfortable processes for technology that might still seem unproven or risky.
The if it ain't broke, don't fix it mentality, even if it is kind of broken.
Exactly. This creates a powerful chicken and egg dilemma. Startups need to achieve scale to drive down costs, prove their ROI convincingly, and build confidence in the market. But they can't achieve that scale without a mature ecosystem supporting them, and crucially, a customer base willing to overcome those initial hurdles, embrace the change, and take that leap of faith.
So what does this all mean for the robotics industry as a whole? You've outlined four very distinct, very difficult challenges. It sounds like a minefield.
Ultimately, running out of money, while often cited as the cause of death, is rarely the root cause. It's usually the final symptom. The underlying disease is a systemic misalignment between the technology, the market needs, and the business strategy. It often begins with that ecosystem immaturity, which inflates R&D costs from day one. This puts immense pressure on the startup to find a market quickly. This pressure can cause technically focused founders to rush out a product that is technologically interesting, but maybe not commercially necessary,
Yeah.
resulting in that vitamin product with poor market fit.
Right.
This weak value proposition then makes it nearly impossible to construct a viable business model that delivers clear, rapid ROI to the customer, which, in turn, makes fundraising harder, eventually depleting capital and leading to failure.
It's a vicious cycle.
It's a brutal cycle. It truly underscores how interconnected these challenges are, making success far more complex than just building cool tech. It requires navigating all these fronts simultaneously.
That's a truly sobering breakdown of the business and market challenges. It sounds like a minefield just to get a robotic startup off the ground. But even if a company somehow navigates all those landmines, what about the technology itself? We hear all this hype about AI, machine learning, reinforcement learning, and robotics. Are they actually living up to the promise? Or are there fundamental technical bottlenecks like this sim-to-real chasm I keep hearing about that stop them in their tracks?
Excellent question. And yes, the technology gap itself is a huge, often underestimated contributor to these failures. Much of the excitement in modern robotics, especially over the last decade, has been tied to AI, and particularly reinforcement learning, or RL. This is a powerful paradigm, right, where an agent learns optimal behaviors through trial and error, interacting with its environment, much like DeepMind's AlphaGo mastered the game of Go.
Learning by doing, essentially.
Exactly. But current RL, as powerful as it is in simulated or constrained environments, has intrinsic limitations when you try to apply it directly to the real physical world. And these limitations lead directly to the sim-to-real chasm, which is perhaps the single greatest technical filter or bottleneck in modern robotics today.
Okay, so reinforcement learning, where the robot learns by trying things out, sounds intuitive. But what are these intrinsic limitations when you try to apply it to a physical robot walking around a factory or a home?
Let's delve into them. The most significant one is its sample inefficiency. RL algorithms need a staggering amount of data. We're talking millions, sometimes even billions, of interactions with an environment to learn an effective policy, a way of behaving.
Billions, with a B.
Sometimes, yes, for complex tasks. Now, for a physical robot, collecting this volume of data through real-world trial and error is impractical at best and often completely impossible. Imagine a robot trying to learn to assemble a complex product by randomly fumbling with parts for years. It would take a physical robot operating 247 potentially years to collect the sheer amount of experience that an RL agent can gain in just a few hours or days inside a fast computer simulation.
Right, the simulation can run much faster than real time.
Exactly. And the real-world process isn't just time-consuming. It's incredibly costly. You have physical wear and tear on expensive hardware, energy consumption, the risk of damage, and potentially the need for constant human supervision. This fundamental inefficiency makes pure trial and error learning on a real robot a non-starter for all but the simplest, most repetitive tasks.
So if I'm understanding this correctly, it's like trying to teach a toddler how to ride a bike by letting them fall countless times on real pavement, risking serious injury, instead of practicing endlessly in a safe, simulated environment first. The sheer cost and risk make it impractical.
Precisely. That's an excellent analogy. The real world is just too slow, too expensive, and too unforgiving for that kind of brute force learning, which is why simulators become so crucial. But that, ironically, opens up a whole new set of formidable challenges.
Okay, so sample inefficiency is one big hurdle. What else limits RL in the real world?
A second major challenge in RL is designing the reward function. This is the signal, the feedback that guides the agent's learning process, telling it what behaviors are desirable and should be reinforced. Crafting a reward function that accurately captures the desired outcome without creating unintended loopholes is notoriously difficult. It's an art as much as a science.
Loopholes. Like the AI finds a way to cheat the system.
Exactly. It's called reward hacking. It's like when you try to incentivize a child to clean their room, but you just reward them for moving the toys quickly. They might just push everything into a pile in the corner and collect their reward without actually tidying up properly. The robot does the same. It finds a clever way to maximize the reward signal without achieving the true objective. For instance, a cleaning robot might learn to just spin in circles in a clean area to maximize time spent cleaning without actually covering the dirty floor, if the reward is poorly designed. And in what are called sparse reward environments, where the robot only receives feedback at the very end of a long, complex task, like successfully assembling an entire device, it might never get enough positive signals during the process to learn anything useful at all. It's just wandering blindly.
That sounds incredibly frustrating to design. And what about adaptability? If the robot learns one specific task, how well does it transfer that skill to a slightly different situation? Can it generalize?
That brings us to the third key limitation. RL models often suffer from poor generalization and transferability. A policy, the learned strategy, that works perfectly for one specific task or in one specific environment often fails catastrophically when conditions change even slightly. Imagine an RL agent trained meticulously to pick a specific red block from a bin. It might fail completely if the block is blue instead, or if the lighting in the room shifts subtly, or if the bin is placed at a slightly different angle.
So it's brittle.
Very brittle. Think about a self-driving car trained only in sunny, clear weather in California. It might perform dangerously in rain, snow, or the chaotic streets of Mumbai. This lack of robustness means that extensive retraining, potentially from scratch, is required for each new task or environmental variation. This makes RL solutions difficult and expensive to scale in the messy, unpredictable real world.
Okay, so real-world training is inefficient, reward functions are hard to design, and the learned skills don't generalize well. That paints a tough picture for RL.
So that's where simulation comes in, right? You train the robot virtually. But then you mention this sim-to-real gap, What exactly is that, and why is it such a formidable challenge, this great filter?
You hit on the core problem. Simulation is indeed the go-to solution for generating the massive data sets that RL needs. It offers a safe, fast, parallelizable, and scalable way to train complex policies. However, this approach introduces what is arguably the single greatest bottleneck, the biggest headache in the field today, the sim-to-real gap.
Hmm.
This term describes the significant degradation in performance, or often outright failure of a policy when it's transferred from the perfectly controlled, clean, virtual world where it was trained to a physical robot operating in messy, nuanced reality.
Ah,
Startups with incredibly impressive simulation demos, videos that look like science fiction, often hit a very hard wall here. What works beautifully on screen often falls apart completely when they try it on the actual hardware. Why? What are the primary reasons for this chasm? Is it about the physics being wrong in the simulation, or how the robot sees the world?
it's both and more. The chasm is really composed of several deep fissures, you could say. First, there's the dynamics mismatch. Simulators are, by definition, approximations of reality. They use mathematical models to represent physics, but they struggle to perfectly model the complex, often chaotic physics of the real world. This includes crucial physical properties like friction, which is notoriously hard to model accurately, inertia, damping, the elasticity of materials, and the intricate dynamics of contact and deformation, especially when things happen quickly.
Stuff that just happens naturally in the real world is hard to code.
Incredibly hard to get exactly right. A policy that learns to exploit the simplified or slightly incorrect physics of a simulator, for example, if a virtual object has no friction and just slides perfectly into place, will inevitably fail when confronted with the nuanced and noisy dynamics of a real robot's motors, its joints, its actuators, and its interaction with actual physical objects that have texture, weight, and imperfections. The real world has rough edges that the simulator smooths over.
Okay, so the physics aren't quite right. What else?
Then there's the sensory mismatch. A robot's ability to perceive the world it senses are just as critical as its ability to move. Policies that rely heavily on sensory input, particularly vision from cameras, are highly susceptible to the sim-to-real gap. It's incredibly challenging, computationally expensive, to create computer-generated images that perfectly replicate all the subtle properties of real-world light and surfaces. Subtle differences in lighting conditions, shadows, textures, reflections, the properties of the camera lens itself, sensor noise. Any of these discrepancies between the simulation and reality can be enough to completely confuse a vision-based policy that was trained solely on simulated images.
So a robot trained on these pristine, perfect computer graphics might be utterly lost when trying to identify the same object under the variable, imperfect lighting of a dusty warehouse, or even just in a room with direct sunlight streaming in.
Precisely. It hasn't learned to handle that visual variability and noise. It's like it's wearing sunglasses that filter out all the imperfections it needs to deal with.
So even tiny visual differences between the virtual and real world can completely derail the robot. That sounds incredibly frustrating for the engineers.
It is. And finally, beyond physics and sensors, we have the broader reality gap and unmodeled effects. The real world is infinitely more complex than any simulation could ever hope to be. It's filled with unforeseen corner cases, subtle phenomena, and random events that are impossible to model exhaustively. This could be anything from the slight sagging of a power cable over time that the robot snags on, to a subtle change in an object's surface properties due to dust or wear, or the unpredictable behavior of humans walking through the robot's workspace.
Stuff you just can't plan for.
Exactly. A policy trained in a sterile, predictable simulation is inherently brittle. It simply lacks the common sense reasoning, the adaptability to handle the messy, unpredictable nature of reality. It hasn't seen the unexpected, so it doesn't know how to react gracefully.
And the consequences for startups trying to commercialize this.
Severe. A company might raise millions of dollars based on a compelling video showing their robot performing a complex task flawlessly in simulation. Looks amazing. The investor's clock starts ticking immediately. The team then spends months, maybe even years, struggling desperately to make that exact same policy work reliably on the physical hardware. This involves painful, expensive cycles of heart. Collect a small amount of real-world data, attempt to fine-tune the simulated model, which is hard, identify the specific physical or sensory mismatches causing the failures, then go back and try to improve the fidelity of the simulator itself, a complex process known as system identification. Rinse and repeat.
Burning time and money with each cycle.
Exactly. This unforeseen and often drastically underestimated R&D effort is a huge form of technical debt. It directly drives business failures by burning through capital far faster than planned and causing missed milestones and product delays.
Okay, so how are researchers and companies trying to bridge this gap? Are there strategies to mitigate this sim-to-real problem?
Yes, there's a lot of active research, and several mitigation strategies are used, though none are perfect silver bullets. One common technique is domain randomization. The idea here is to train the agent in simulation across a wide range of randomized physical and visual parameters.
Like making the simulation less perfect on purpose.
Exactly. You vary things like friction coefficients, object masses, lighting conditions, textures, camera positions within certain bounds during training. The hope is that by exposing the policy to so much variation in simulation, it learns to be more robust and less sensitive to the specific parameters it encounters in the real world. It learns a strategy that works across many variations.
Makes sense. What else?
Another approach is domain adaptation. This involves techniques to explicitly learn a mapping or relationship between the simulated domain and the real domain. This might involve fine-tuning models trained in simulation using smaller data sets collected from the real world, or using techniques like generative adversarial networks, GANs, to make simulated images look more realistic, tricking the policy into thinking it's seeing real data.
Trying to make the simulation look more like reality, or teaching the robot to translate between them.
Correct. There's also imitation learning, IL, and meta-learning. IL can bootstrap the learning process by using human demonstrations or traditional non-learning controllers to guide the initial exploration, reducing the need for purely random trial and error, which is so inefficient. Meta-learning aims to train models that can adapt quickly to new tasks or environments with very little additional data. And of course, there's ongoing work on just building better simulators, improving the physics engines, creating more photorealistic rendering, using techniques like neural radiance fields, NeurFs, trying to capture more of that real-world complexity.
So lots of different angles trying to tackle this.
Yes, but despite all this active research and these clever strategies, the sim-to-real chasm remains a fundamental, largely unsolved problem in robotics. Each mitigation strategy adds its own complexity and computational cost. And for a startup under immense pressure to deliver a working product, the journey from that impressive simulated demo to a reliable, robust, real-world system remains perilous and uncertain. It's still where many dreams die.
It sounds like a truly brutal technical landscape. That sim-to-real gap really is a graveyard. But given the current state of AI, especially with large language models becoming so incredibly powerful, is there hope? Is AI finally offering a way to truly close this chasm, or at least build a stronger bridge? How is this revolution we're seeing in, say, video understanding changing things for robotics?
This is exactly where the story pivots to incredible promise, Nikhil, and where recent breakthroughs are truly transformative, offering a path around some of the limitations we just discussed. The convergence of advanced AI, particularly sophisticated video understanding with robotics, is truly revolutionary. It's fundamentally about giving robots eyes that can not only see but understand the world in a much richer way. This enables them to learn in ways previously unimaginable, moving beyond the brittle policies learned from pure RL or simulation alone. And crucially, as a side effect, it's also making robotics much more accessible to new talent, broadening the pool of innovators who can contribute.
You mentioned accessibility to new talent. How is that happening? I always thought robotics was still a very niche, difficult field to just jump into.
The good news is that foundational learning in robotics is rapidly democratizing. The field, once largely confined to specialized labs and industrial settings, is now becoming much more accessible. This is thanks to a wealth of online learning resources. Top universities like Stanford and MIT offer comprehensive programs online, many with lectures available for free through platforms like OpenCourseWare. Think of Russ Tedrake's courses at MIT on manipulation and underactuated robotics, legendary stuff, now widely accessible.
So university-level knowledge is out there.
Absolutely. And beyond top universities, you have accessible MOOCs, massive open online courses and specializations on platforms like Udacity, Coursera, and EDX. Sebastian Thrun's Artificial Intelligence for Robotics on Udacity requires almost no prior experience. Coursera has Northwestern's Modern Robotics specialization. ADX has Penn's courses on kinematics. There are even courses focused on robotic process automation, RPA, which is slightly different but related.
Wow, okay, so lots of structured learning paths.
And it's not just formal courses. There are engaging video lectures and channels on YouTube. Stanford's CS223A lectures are there, MIT OpenCourseWare channels, Russ Tedrake's personal channel, channels from India like NPTL. Plus, you see amazing practical demonstrations from companies like Boston Dynamics and tutorials from channels like PRO Robots, Learn Robotics with Liz. It offers free, practical insights and tutorials for beginners.
So the barrier to entry for learning the fundamentals is much lower now.
Much lower. Regardless of the path someone takes, the core concepts are becoming widely teachable. The essential math like linear algebra and calculus for kinematics and dynamics, programming, especially Python for its readability in libraries and C++ for performance, and the core robotics topics themselves, kinematics, dynamics, control systems, perception, motion planning. This democratization ensures a growing talent pool is emerging, ready and equipped to tackle these advanced challenges we're discussing. It brings fresh perspectives and more hands-on experience into the field faster.
That's fantastic for the future of the field. So with this growing talent pool, what are the big technological leaps they're leveraging? You mentioned video understanding.
Right. Speaking of advanced challenges, the biggest leap, the one truly addressing the brittleness and generalization problems and the sim-to-real chasm, is in how robots see and understand the visual world. This is the dawn of robotic vision. At its heart are foundation models. We hear this term a lot now. These are large-scale machine learning models, often based on the transformer architecture, the same tech behind models like ChatGPT, trained on vast, diverse datasets, including massive amounts of images and video. They learn general-purpose representations of the world. This allows them to adapt to specific downstream tasks with minimal task-specific fine-tuning. They can often perform a zero-shot or few-shot learning from zero, or just a few examples. And importantly, they can often be guided by human prompts or instructions.
So these foundation models give robots a kind of general visual understanding of the world, like a baseline intelligence they can build on, rather than learning every visual concept from scratch.
Precisely. It's
Yeah.
a huge efficiency gain. And building on that, we have vision language models, VLMs, and their extension, vision language action, VLA models. VLMs, like OpenAI's CLP, learn to bridge visual information and textual descriptions. They learn to associate what they see in an image or video frame with language. This allows robots to understand natural language instructions related to the visual scene, like pick up the red block next to the blue cup. They can also describe their surroundings, answer questions about what they see, and engage in much more intuitive human-robot interaction.
So you can talk to the robot about what it's seeing.
Exactly. And VLA models, like Google's RT2, Robotic Transformer 2, take this a critical step further. They don't just understand, they act. They directly generate robot actions based on combined visual and linguistic input. This is a game changer for robot control and flexibility. It allows robots to follow much more nuanced, abstract, and natural commands, generalizing to new objects and situations described in language.
That sounds like it gets closer to how humans operate, see, understand, act based on goals. What about understanding the physics of what they see?
That's a huge and significant frontier. Extracting deeper insights, understanding physics and science from videos, not just what is happening, but why it's happening. As we discussed, current generative video models can create visually realistic scenes, but they often lack physical plausibility. A generated ball might float through a wall, defying gravity. Researchers are actively working to imbue AI with physical common sense. This can be done implicitly by having models observe massive amounts of real-world video data and learn the patterns of physics, or explicitly by incorporating physical laws and constraints into the model architecture or training process.
Like teaching the AI physics.
Essentially, yes. For example, some models like Video RePA try to distill physical understanding from large video understanding foundation models into smaller, more efficient models. Others like Diffie focus on fine-tuning video diffusion models to be explicitly physics-aware using guidance from multimodal large language models, MLLMs. Importantly, benchmarking tools like Physics IQ are emerging. These test a model's ability to predict future states based on physical principles observed in videos, ensuring that what the robot sees and predicts aligns with how the physical world actually works.
So we're talking about robots that don't just recognize objects, but have an internal model of how those objects behave in the real world, based on learned physical laws. That's a massive leap from just pattern matching.
It absolutely is. It's about moving towards understanding causality. And then you have powerful advancements in 3D scene understanding using techniques like neural fields. These are frameworks like occupancy networks, sign distance fields, SDFs, neural radiance fields, neuropholephs, and Gaussian splatting. They learn continuous representations of a scene's geometry and appearance directly from 2D images.
Creating a 3D map from 2D pictures.
Think of it as creating an incredibly detailed, implicit 3D map or model of the environment from what the robot sees through its cameras. These are invaluable for tasks requiring precise spatial understanding. Things like accurate pose estimation of objects, detailed 3D reconstruction for complex manipulation tasks, building accurate maps for navigation, and even simulating physical interactions within that learned 3D representation. They offer a much more granular, flexible, and often differentiable way for robots to model and reason about their 3D surroundings.
Okay, that's deep tech. And how does this tie back into the large language models like ChatGPT?
This is the final piece of the puzzle. Video is emerging as a critical new data source for LLMs themselves. Video understanding models act as the eyes for LLMs, providing them with a rich, dynamic window into the visual, physical world. They translate complex visual scenes into text descriptions or structured data that the LLM can then process and reason about. Frameworks like the Multimodal Video Understanding (MVU) framework use various vision tools to extract details about objects in videos, their identity, location, trajectory, and convert this information into natural language summaries for LLMs.
Giving the LLM situational awareness.
Exactly. This enables the AI to build a dynamic knowledge base, continuously updated with information about the physical world observed through video. It's not just static knowledge from text anymore. And it enables real-time conversational interactions about live video streams. Think of Google's demos with Gemini understanding a live video feed, or models like StreamChat designed to handle the context of streaming video for interactive Q&A.
So this convergence is pivotal. Video understanding gives LLMs eyes, grounding their abstract linguistic knowledge in concrete visual experiences. Conversely, LLMs provide high-level context, reasoning, and goal-setting capabilities to guide the interpretation of visual data and generate actions.
You've got it. It's the basis for the next generation of truly intelligent agents and robotic systems. It directly addresses the generalization and robustness issues that plagued earlier RL models by leveraging vast world knowledge and reasoning capabilities. It's fundamentally changing the landscape of what's possible in robotics.
That's incredible. So this isn't just theoretical research confined to labs. It sounds like these capabilities, especially video understanding, are already making a tangible difference out there. How are these advancements transforming industries and maybe even aspects of daily life right now? And crucially, how do these powerful AI advancements tie back into creating successful, viable business models for those robotic startups trying to beat the odds?
You're right. The applications are truly diverse and exciting, moving robots far beyond just sterile industrial settings. And yes, this advanced AI is absolutely fundamental to the new business models that are proving to be more viable. Let's look at some of these real-world revolutions first. Take sports analytics, for example. AI is completely transforming how we analyze and understand games. Video understanding models meticulously analyze player movements, ball trajectories, specific actions like a tennis serve or a basketball shot. This provides coaches and teams with enhanced performance analysis, deep tactical insights, automated scouting of opponents or potential recruits, and even helps with injury prevention by identifying risky biomechanical patterns.
So much more data than a human coach could track.
Orders of magnitude more. For example, the ViceTech model uses visual features extracted from video to analyze stroke techniques in racket sports, identifying personalized characteristics of a player's swing automatically. Tools like SportsBuddy can even generate automated highlights and narrative summaries of games by combining player detection, pose estimation, action recognition, and AI captioning using models like GPT-4o. This gives coaches, broadcasters, and fans much deeper and faster insights.
That's a fascinating application, almost like having an AI co-coach analyzing every angle.
Right.
What about applications closer to home, in everyday life?
Well, then there's AI in everyday life, from kitchens to daily chores. The long-held dream of home robots that can actually help out with complex, unstructured tasks is finally starting to become real, thanks to video understanding. Robots are now learning household chores simply by observing human videos online or demonstrations in a lab. This often involves what are called large behavior models, or LXMs, think LLMs, but for actions, allowing robots to learn complex, multi-step action sequences and adapt them to various home environments without needing explicit step-by-step programming for every situation.
Learning by watching, like humans do.
Exactly. Researchers at Carnegie Mellon, for example, have demonstrated robots learning various chores just by watching people perform them in their homes on video. Toyota Research Institute is even teaching robots intricate tasks like peeling vegetables using generative AI by analyzing video demonstrations of humans doing it. DeepMind has shown robots learning to open drawers, stack blocks, and perform other simple manipulation tasks purely from observing human demonstrations. The ultimate goal here is creating general-purpose robots that can operate reliably and usefully in the unpredictable, unstructured environments of our homes.
The Rosie the Robot's dream edging closer.
Maybe not tomorrow, but the path is becoming clearer. Another critical application is advancing autonomous vehicles. Safe and reliable self-driving cars rely heavily on interpreting complex, dynamic road environments in real time. Video understanding models, often incorporating techniques from VLMs like CLIP, are crucial for this dynamic scene understanding. They allow the vehicle to classify road conditions, wet, icy, etc., accurately identify and track objects like other vehicles, pedestrians, cyclists, traffic lights, and crucially, predict their future movements and intentions.
Understanding the whole context, not just objects.
Right. This dramatically improves safety and reliability, helps autonomous systems understand nuanced and sometimes irrational human driver behavior, and is absolutely crucial for building public trust in AV technology. Datasets like the Honda Scenes dataset are specifically designed to help fine-tune these models for better scene classification accuracy in diverse driving conditions encountered worldwide.
It seems like a lot of this hinges on having massive amounts of good, diverse training data. How is AI itself helping with the huge task of data collection and labeling for these models?
You're absolutely right. Data is the lifeblood of modern AI, and this capability is fundamentally revolutionizing research and data collection itself. Training robust AI models for robotics, especially those foundation models, requires vast amounts of diverse, accurately labeled data. Manually creating these datasets is painstaking, incredibly time-consuming, expensive, and prone to human error and bias.
The bottleneck used to be data annotation.
A huge bottleneck. Now, AI, particularly generative AI and sophisticated video understanding techniques, is automating large parts of this process. Initiatives like the NVIDIA Physical AI dataset provide large volumes of both real-world and physically realistic synthetic video data for training robot policies, reducing the need for costly manual data collection in the real world. Tools like NVIDIA Nemo Curator can process and curate massive unlabeled video datasets efficiently, extracting useful information. And NVIDIA's Isaac Geo0T project uses synthetic motion generation from human demonstrations captured on video to create extensive, diverse datasets for robot manipulation tasks, generating endless variations that would be impossible to collect manually in the real world.
So AI is helping create the data to train better AI.
Exactly. Furthermore, robots are now learning skills by observing unlabeled in-the-wild online videos like those found on YouTube or other platforms. Projects like VidBot from Berkeley have shown robots learning tasks like closing refrigerator doors or wiping counters just by watching human videos through imitation learning without any explicit labels. Deep learning models like SSD and Inception are fundamental for object recognition and tracking within video streams, essential for both robot environment understanding and for researchers looking to automatically collect specific types of data from large video archives. Projects like RoboBrain aim to build large knowledge graphs for robots by processing web data, including videos. This creates a powerful virtuous cycle, a data flywheel, where better video understanding leads to better automated data generation and curation, which in turn leads to more capable AI models, which leads to better understanding, and so on.
That data flywheel concept is powerful. It accelerates progress. So, with all these technological advancements driven by video understanding and AI, how are robotics companies actually leveraging them to succeed? What are the new blueprints for building a viable robotics business that avoids that dreaded 99% failure rate?
Excellent question. Let's talk about the blueprints for success that are emerging, often directly enabled by these AI advancements. The most significant shift is arguably in business model innovation, the rise of robot as a service, RaaS. This is a truly game-changing model that directly addresses both the capital chasm, the high upfront cost, and the business model void, the lack of proven commercialization strategies that we discussed earlier. Instead of a customer making a massive upfront capital expenditure, CapEx, to purchase a robot, they essentially lease the robotic solution, often on a subscription or pay-per-use basis. It shifts the cost from CapEx to operational expenditure, OpEx.
So it's like subscribing to Netflix but for a warehouse robot. You pay for the service, not the hardware itself.
Precisely. That's a great analogy. For customers, RaaS dramatically lowers the financial barrier to entry. This makes sophisticated automation accessible even for small and medium-sized enterprises, SMEs, that simply couldn't afford to buy a fleet of expensive robots otherwise. It also significantly reduces their risk. They're not locked into owning potentially obsolete hardware in a few years, and crucially, the RaaS provider typically handles all the complex stuff: maintenance, software updates, support, and sometimes even the initial integration.
That sounds much more appealing for a customer. What about the robotics company?
For the robotics companies themselves, RaaS creates predictable, recurring revenue streams. This is far more attractive to investors in bed for financial planning than lumpy, unpredictable hardware sales. It's estimated that RaaS models can boost the customer lifetime value, LTV, by around 34% over 5 years compared to traditional outright sales. And, very importantly, it aligns incentives beautifully. The startup only makes money consistently if the robot is actually working, delivering value, and staying operational for the customer.
Right, if the robot breaks down, the provider loses revenue.
Exactly. Their success is directly tied to the customer's success with the robot. This model can even help shorten those historically long sales cycles, as the initial commitment is less daunting for the customer, allowing robots to get deployed and start generating value faster. The market is reflecting this shift. The RaaS market is projected to reach something like $4 billion by 2028, growing at a healthy 17.5% compound annual growth rate, CAGR. That shows its rapid adoption. You see real examples. Richtech Robotics, which makes service robots, apparently doubled its number of installations after switching its main offering to RaaS in 2024. Locus Robotics, a major player in warehouse automation AMRs, autonomous mobile robots, operates purely on a RaaS model. Scythe Robotics, offering autonomous lawn mowing for commercial landscapers, uses usage-based billing per acre mode.
So RaaS is definitely a key part of the emerging success blueprint. What else?
Another crucial blueprint is vertical-specific solutions. Increasingly, the successful startups we see are focusing intensely on specific industry verticals like healthcare logistics or warehouse fulfillment or specialized agriculture tasks or a particular type of manufacturing process rather than trying to build general-purpose robots designed for everyone. Micropolis Holding Company, for example, is developing autonomous mobile robots specifically tailored for the needs of the security sector, the hospitality industry, and last-mile logistics. They're not trying to build one robot for all three.
Going deep, not broad.
Exactly. This focused approach allows them to develop deep domain expertise, truly understand the specific customer pain points and workflows within that niche, and tailor their hardware, software, and crucially, their AI models accordingly. This focus also resonates strongly with investors. Back in 2024, a significant chunk, something like 62% of venture capital invested in robotics, flowed into these vertical plays rather than broad, general-purpose robotics platforms. Investors like that focus.
So instead of trying to be everything to everyone, they're becoming the absolute best at solving one very specific high-value problem. That makes a lot of strategic sense. And what about innovation on the tech stack itself? How are successful companies building their robots differently?
That brings us to technology stack innovation, specifically leveraging modular platforms and next-gen AI. Modular robotics platforms are emerging as a direct solution to that ecosystem immaturity problem we discussed, where every startup previously had to reinvent the wheel for basic components. Companies like Omnilabs, Habe Robotics, or even component suppliers like IGIS are providing pre-engineered, standardized building blocks, things like actuators, controllers, sensors, frameworks with APIs.
Like Lego bricks for robots.
Kind of, yes. Startups can select and integrate these reliable, pre-tested modules to build their application-specific robot much faster and with lower R&D cost. They can bypass a lot of that painful, time-consuming hardware, software Frankenstein debugging process for the core platform. This allows them to focus their limited engineering resources and capital on their unique value proposition, the specific application, the clever manipulation, the specialized AI, rather than the foundational plumbing.
That seems like a much smarter way to build. And the AI part.
And this ties directly into leveraging next-gen AI, going beyond pure traditional reinforcement learning. As we discussed earlier, those vision language action, or VLA, models being developed and deployed by companies like Figure AI with their humanoid robot or Google DeepMind with their various robotics projects are transformative. These models can interpret high-level natural language commands, bring me the apple from the counter, and translate them into complex action sequences, often generalizing to novel objects and tasks they weren't explicitly trained on.
Using language to unlock flexibility.
Precisely. This directly attacks RL's historical weaknesses: sample inefficiency and poor generalization. It promises far more flexible, adaptable robots that require significantly less task-specific training data and engineering effort. Imagine telling a factory robot in plain English to reconfigure the assembly line for the new product model and having it understand and execute the necessary steps.
Yeah.
That's the power VLA models are beginning to unlock.
Those are really powerful strategies. RaaS, vertical focus, modularity, next-gen AI. Are there any classic success stories, maybe comparing companies, that really exemplify these new blueprints in action?
Absolutely. If we look back at some success case studies, the contrast between Universal Robots, UR, and Rethink Robotics is illustrative. Universal Robots is a prime example of the pragmatic problem solver. Their success against Rethink, which was arguably more technologically ambitious initially, came down to focus. UR targeted a specific, acute problem for SMEs, making collaborative automation accessible, easy to program, and affordable enough to solve real labor shortages and productivity bottlenecks. They prioritized ease of use. Their programming interface was revolutionary simple at the time. They had a very clear value proposition. And they strategically built an ecosystem around their product with the UR Plus platform, encouraging third-party developers to create grippers, sensors, and software that extended their cobot's capabilities. They focused on solving the customer's problem holistically.
While Rethink was maybe more focused on the tech itself initially.
Arguably, yes. Their initial focus on Baxter's low price point led to performance compromises, making it more of a vitamin. UR delivered the painkiller that SMEs needed. Then you have a company like Boston Dynamics. They represent the deep tech powerhouse model. They had a very long patient R&D history, heavily supported by DARPA funding initially. This allowed them to build truly unmatched, defensible technology in dynamic mobility and agility. Their robots can go places others simply can't.
Their videos are amazing.
They are. They target highly unstructured, often dull, dirty, or dangerous environments where their unique capabilities shine. Think construction sites, nuclear power plants, disaster zones, industrial inspection. Their technology is the core differentiator. But even they have adopted a flexible commercial model, offering their robots like Spot through direct sales, leasing options, and service contracts. This generates crucial recurring revenue from ongoing support, software updates, and specialized payloads, moving beyond just selling the hardware.
So even the deep tech leader sees the value in service-based models. It really seems like the key takeaway is it's not just about building the coolest robot anymore. It's about how you package it, how you target it, how you sell it, and how you sustain it financially.
Exactly. The winning combination seems to be RaaS, or similar service-oriented models, coupled with modular platform strategies for efficiency, powered by next-generation AI for capability and flexibility, and laser-focused on specific vertical markets with clear pain points. This combination systematically de-risks the venture at multiple levels. It allows startups to get to market faster, often with less upfront capital required, and offers solutions that are significantly easier for customers to adopt, integrate, and scale because the initial burden is lower and the path to value is clearer. This is really the new investment thesis emerging in robotics. Bet on focused, commercially savvy teams leveraging these integrated strategies, not necessarily on the most technically ambitious full-stack attempts to solve everything from the ground up.
This has been incredibly insightful. You've really illuminated a clear path through what initially seemed like an almost impossible robotics gauntlet. We've gone from the 99% failure rate to understanding the blueprints for success. So let's distill this down. If someone listening out there is dreaming of starting their own robotics company, or perhaps looking to invest in this space, what are the most critical, actionable takeaways? What are the absolute must-dos based on everything we've just discussed?
Great question. For founders, the core message is about finding that delicate balance between groundbreaking technical ambition and hard-nosed commercial pragmatism. For investors, it requires adopting a new lens, a more nuanced framework for evaluating these unique ventures. Let's start with founders. The first, and I cannot stress this enough, the absolutely most crucial piece of advice is focus on the pain, not just the tech. You absolutely must fall in love with solving a high-value customer problem first, not just with the elegance or novelty of your technology.
Problem first, solution second.
Always. Before you write a single line of code or machine, a single prototype part, you must validate rigorously that you are building a painkiller for a specific, well-defined niche, not just a cool general-purpose vitamin. This means deep, relentless customer discovery is non-negotiable. Get out of the lab. Talk to potential users. Understand their workflows intimately, their biggest bottlenecks, their most urgent challenges, and crucially, the economic value they would place on solving those problems. Without that deep understanding, you're essentially building blind.
So even if your robot can theoretically do a million amazing things, if it doesn't solve one critical, high-value problem exceptionally well, it's likely a dead end commercially.
Precisely. Nail a niche first. Second piece of advice for founders. Embrace lean hardware development. The classic software mantra of move fast and break things needs careful adaptation for the physical world, where breaking things is expensive and slow. Adopt an MVP minimum viable product strategy relentlessly. Focus only on the core features that directly solve the customer's primary pain point in the simplest, most reliable way possible. Resist the engineering urge to add bells and whistles early on.
Keep it simple, stupid.
Yeah.
KISS.
The KISS principle applies strongly here. And aggressively leverage those modular robotics platforms we talked about, the pre-engineered components, the standardized frameworks. Use them wherever possible to significantly reduce your R&D costs and timelines, and avoid reinventing foundational components that don't differentiate you. Crucially, integrate design for manufacturability, DFM principles, from the absolute earliest stages of your design process. Think about how this thing will actually be built at scale, how it will be assembled, tested, and maintained right from day one. This prevents those costly, time-consuming, sometimes fatal redesigns later on when you realize your beautiful prototype is impossible or too expensive to manufacture reliably.
Thinking about production from the start, not as an afterthought.
Essential for hardware. Third, build a balanced and resilient team. A team stacked with brilliant PhD engineers is absolutely necessary, but it is profoundly insufficient for success. From day one, your founding team needs complementary and, importantly, co-equal strength on the business side. You need dedicated, experienced leadership focused exclusively on go-to-market strategy, sales, marketing, partnerships, and finance.
Not just engineers running the whole show.
Definitely not.
Yeah.
A purely technical founding team is structurally almost destined to fall into that product over business trap we discussed earlier, where perfecting the technology endlessly overshadows achieving commercial viability and market traction. You need that constant push and pull between what's possible technically and what's needed commercially. And finally, on the team point, resilience is paramount. Building a robotic startup is an incredibly demanding marathon, not a sprint. The challenges technical, financial, market are relentless. The team needs the fortitude, the grit, the ability to withstand immense pressure and navigate the inevitable emotional roller coaster together.
That's a great point. It's not just about the robot. It's about the people building the company around the robot and their ability to endure.
Couldn't agree more. Fourth, architect a viable business model from the very beginning. Do not treat it as an afterthought tacked on once the tech is ready. The traditional model of selling expensive hardware up front, as we've seen, is a high-friction approach that has been the downfall of many promising robotics companies. Seriously consider and deeply analyze a robot as a service, RaaS model, or similar recurring revenue approaches. They demonstrably lower customer adoption barriers, create more predictable revenue streams, and align your incentives with your customer's success. Whichever model you choose, you must have an intimate, almost obsessive understanding of your unit economics, your cost of goods sold, COGS, your customer acquisition costs, CO, your lifetime value, LTV. And you must be brutally realistic about the demanding cash flow cycle dictated by building and deploying physical inventory. Hardware requires significant upfront investment before you see revenue, a key difference from pure software plays.
Know your numbers inside out.
Absolutely. And fifth, perhaps counterintuitively for some engineers, be a sophisticated storyteller. Fundraising, customer acquisition, recruiting top talent. It's not just a technical bake-off based on specs. It's fundamentally about articulating a compelling, coherent narrative. A story that connects your technology to solving real-world problems for specific people and tapping into a significant market opportunity. Investors, customers, employees, they are backing a vision, not just a collection of features on a spec sheet. And critically, support the story with tangible evidence. Data from pilot programs, metrics showing ROI, and genuine customer testimonials are far more powerful and credible than even the most polished simulation videos. Nothing speaks louder than real customer success and validation.
So it's a powerful combination of deep substance, the tech, the market understanding, the business model, and effective storytelling to convey that substance. What about for the investors listening? How should they approach this complex space? What should they prioritize when evaluating opportunities?
Now, turning to investors, navigating the robotics landscape requires, I believe, a specific thesis, a tailored approach distinct from standard software investing. First, and perhaps most importantly, evaluate the founder and the entire team, not just the robot itself. In a field this complex and challenging, the quality, balance, and resilience of the founding team are arguably the single most important predictors of long-term success. Look for founders who possess not only undeniable technical brilliance, but also deep business acumen, genuine market insight, and humility. Assess the team's balance carefully. Is there disproportionate focus on academic or engineering credentials without corresponding experience leadership in business development, sales, and operations? That's a major red flag. Have they actually done the hard work of customer discovery, or are they just assuming they know what the market needs?
Betting on the jockey, not just the horse.
Exactly. Second, prioritize software, data, and scalability. In the long run, hardware tends to commoditize. The enduring value, the defensible competitive moat of a successful robotics company will likely reside in its sophisticated software stack, its proprietary AI models, and the valuable data it collects, which can create powerful network effects. The robots get smarter and more valuable over time as more data is gathered. Scrutinize the startup's software architecture and its strategy for leveraging data to continuously improve performance and deliver increasing value. And critically, assess the scalability of the entire business, not just the technology. How will the company effectively expand its market presence, build partnerships, and support a growing deployed base?
So the hardware might be the initial product, but the real long-term value is in the intelligence, the data, and the ability to scale the whole operation.
That's where the sustainable advantage often lies. Third, scrutinize the go-to-market strategy and the business model rigorously. A technically brilliant robot with no viable, realistic path to market adoption is effectively a worthless investment, no matter how cool it looks. Demand a clear, pragmatic, and detailed go-to-market strategy that explicitly acknowledges the realities of the robotics market, the long sales cycles, the high integration costs, the customer inertia. Be wary of overly optimistic projections that ignore these hurdles, and as we discussed, favor business models like RaaS or other service-oriented approaches. These often demonstrate a more sophisticated understanding of customer adoption barriers and typically provide a clearer, more significant, and more easily achievable ROI for the customer within a reasonable time frame, which drives adoption.
Look for realism and customer centricity in the commercial plan.
Absolutely. Fourth, de-risk the technical bet by understanding the specific challenges. You must explicitly acknowledge that the sim-to-real gap, hardware reliability, and system integration are major sources of both technical and financial risk in robotics. Critically evaluate the team's concrete, data-driven plan to bridge that sim-to-real chasm. Are they relying on hand-wavy optimism? Or do they have a solid, demonstrable approach involving techniques like domain randomization, domain adaptation, extensive real-world testing, and robust system identification? Ask for the data. Also, favor companies that are intelligently building upon existing modular platforms where appropriate, rather than insisting on building their entire technology stack from the ground up. This often demonstrates better capital efficiency and a focus on delivering application value faster.
So dig into the technical mitigation strategies and look for smart leverage of existing tech.
Exactly. And finally, fifth, for investors, be patient but strategic. Robotics is fundamentally not a sector for investors seeking quick flips or rapid software-like exits. It requires patient, long-term capital willing to support companies through lengthy development cycles and market adoption curves. However, patience shouldn't mean blind faith. The most promising investments will likely be in those companies that are systematically de-risking their ventures. They do this by intelligently combining innovative business models like RaaS with smart technology strategies leveraging modularity, adopting next-generation AI, and are laser-focused on targeting clear, high-value enterprise niches where the customer pain is acute and quantifiable, such as in logistics, specialized manufacturing, healthcare services, or precision agriculture. These are the companies, in my view, that have the greatest potential to survive the gauntlet, achieve sustainable traction, and build significant, enduring value over the long term.
That's a fantastic summary of the playbook for both founders and investors. It's clear that the path to success in robotics is about so much more than just groundbreaking tech. It truly is this intricate dance between technology, business savvy, strategic choices, team dynamics, and a deep, empathetic understanding of customer pain points. But looking ahead now, stepping back from the startups themselves, what broader societal impact do you foresee from this powerful convergence of robotics, intelligent video understanding, and AI? How will this change things for all of us?
That's a great question to end on, thinking about the bigger picture. This fusion of robotics, advanced video understanding, and large language models is poised to bring profound changes across society, touching nearly every aspect of human life, both positively and presenting new challenges. One of the most significant and often debated impacts will be on the evolving landscape of work. There's no doubt that AI will continue to transform how work gets done. It will automate many routine or entry-level entry-level tasks, particularly those involving data collection, data analysis, and pattern recognition. The World Economic Forum's Future of Jobs report from a couple of years ago projected that a significant percentage of employers, I think around 40%, anticipated workforce reductions in these types of roles by 2025, with positions like data entry clerks or market research analysts being particularly vulnerable. This could potentially narrow traditional career entry pathways for young people.
So some jobs will likely disappear or be significantly reshaped. But will new ones emerge?
That's the crucial counterpoint. History suggests technological shifts displace some jobs but create new ones. AI is also expected to create entirely new roles and significantly augment existing ones. There will be a growing demand for individuals skilled in developing, managing, deploying, and collaborating with AI systems. AI trainers, AI ethicists, robot supervisors, prompt engineers, data curators. The concept of super agency, where AI acts as a powerful tool to empower human creativity, problem solving, and productivity, suggests a future of synergy rather than pure replacement in many fields. But navigating this transition successfully will require a massive society-wide emphasis on upskilling, reskilling, and lifelong learning. Individuals and organizations need to adapt to this new kind of partnership with technology.
A period of significant adjustment for the workforce. What about impacts beyond employment?
Beyond work, the societal implications are incredibly broad. In terms of accessibility, AI-driven technologies are creating remarkable new possibilities for individuals with disabilities. Think of Google's Project Relate, helping people with non-standard speech communicate more easily, or efforts like the Monk's Skin Tone Scale, aiming to make AI vision systems more inclusive and less biased by improving how they recognize diverse skin tones. In healthcare, the potential is immense. AI is enhancing diagnostic capabilities, helping radiologists spot cancer earlier in scans, detecting diabetic retinopathy from eye images. It's also being used to develop digital tools to assist healthcare workers, reduce burnout, and analyze surgical videos for training surgeons and assessing performance objectively.
Better healthcare outcomes and potentially more efficiency.
That's the hope. In education, AI promises more personalized learning experiences, adapting to individual student needs. Tools like Read Along from Google are helping children improve literacy skills. AI can support educators by automating administrative tasks like grading or generating draft lesson plans, freeing them up for more direct student interaction. And it can foster interest in STEM and AI among young learners through engaging tools. For climate and the environment, AI models are being deployed for more accurate flood forecasting, optimizing traffic flow in cities to reduce emissions, helping track the spread of wildfires, and even aiding in coral reef conservation through analysis of underwater imagery, like in Project Contrails.
Using AI for societal good.
Yes, there's huge potential there. Overall, AI drives economic opportunity and innovation by automating mundane tasks, freeing up human potential, and providing powerful new tools for scientific discovery, analysis, and creation across all fields. And it's revolutionizing content creation and communication, streamlining video production with automated script generation, scene creation, editing, and enabling highly personalized content delivery and interaction.
That's an incredibly broad and mostly positive picture of the potential impact. But with all this rapid advancement, what are the big challenges or risks still ahead? It can't be entirely smooth sailing, even with these amazing breakthroughs.
That's absolutely true. It's crucial to be realistic. Despite this immense potential, the road ahead is definitely not without its significant challenges and potential pitfalls. The performance of these sophisticated models, especially foundation models, relies heavily on data requirements, vast amounts of high-quality, diverse, and critically unbiased data. Curating the necessary in the wild video and other data is challenging, making automated dataset generation and careful bias mitigation crucial for scaling up responsibly. Garbage in, garbage out still applies. There's also the hurdle of real-time performance. The sheer computational intensity of running these huge foundation models can be a bottleneck for applications like autonomous driving or interactive robotics, where split-second decisions and responses are critical. Edge computing and model optimization are key areas of research here.
Making them fast enough for the real world.
Exactly. Generalization and robustness remain fundamental challenges. Ensuring that models reliably generalize from their training data to novel, unpredictable real-world scenarios is still incredibly difficult. How do you guarantee safety when the unexpected happens? Which leads directly to safety and reliability. These are paramount, especially as autonomous systems and robots operate more closely with humans in complex, dynamic environments. We need rigorous methods for verification, validation, and ensuring fail-safe behaviors. The black box nature of many deep learning models makes interpretability and explainability vital. For building trust, for debugging failures, for ensuring fairness, we need to understand why an AI system makes the decisions it does. This is still a major research challenge.
Understanding the why behind the AI's actions.
Critically important. And, of course, there are significant ethical considerations that we must proactively address. Issues surrounding bias embedded in training data leading to unfair outcomes, the potential for large-scale job displacement if transitions aren't managed well, privacy concerns arising from pervasive video surveillance needed for data collection, and the potential for misuse of powerful AI technologies for harmful purposes. These require careful governance, regulation, and ongoing public dialogue. A long-term scientific goal is bridging the gap to true human-like understanding, moving beyond sophisticated pattern recognition to deep causal reasoning about the world, achieving genuine physical common sense. Benchmarks like Physics IQ and EC Bench are vital for measuring progress towards this ambitious goal. And finally, the role of simulation won't disappear. It will continue to be crucially important for cost-effective training, testing safety-critical scenarios, generating synthetic data, and exploring rare edge cases. Bridging that sim-to-real gap effectively and efficiently remains a very active and vital area of research. So yes, it's a journey with immense promise, but one that requires careful navigation of both technical and societal challenges.
This has been an absolutely incredible deep dive, truly revealing the intricate dance between cutting-edge technology like AI and video understanding and the essential, often harsh realities of business strategy in the world of robotics. We've seen the almost unbelievable potential, the significant, often fatal pitfalls, and the innovative solutions and strategies that are now emerging.
Absolutely. The ability of robots to not just see, but to perceive, interpret, and learn from the rich, dynamic visual world around them, that's foundational. It's the key to creating truly intelligent, adaptable systems. This is how we move beyond simple, pre-programmed machines stuck in cages towards robots that can understand natural language, adapt to messy, unpredictable environments, and interact safely and seamlessly alongside us.
It paints a picture of a future where robots aren't just tools, but perhaps intelligent partners or assistants, capable of genuinely augmenting our human capabilities across countless domains, from factories to homes to hospitals. The potential truly feels limitless, despite the challenges. So as we wrap up this fascinating discussion, what's your final provocative thought? Something for our listeners to really mull over from this deep dive into the world of robotics.
A final thought. Okay, here it is. We've talked a lot about how robots are starting to learn complex new skills, physical skills, cognitive skills, simply by watching videos, processing visual data, much like humans do when they learn by observation. So, my question back to the listener is this. If robots can leverage this increasingly accessible wealth of visual and digital information online to learn and transform their capabilities so rapidly, how will you leverage this same accessible ocean of information, the courses, the videos, the research papers, the open source code to transform your own understanding, your own skills, and your own contributions in this rapidly unfolding technological landscape? The knowledge is increasingly out there. The question is, what will you build with it?
That's a powerful thought to end on, a challenge to us all. Thank you so much for guiding us through this fascinating and crucial area today. It's been incredibly illuminating. And thank you, our listener, for joining us on the deep dive. Until next time, keep digging for knowledge.